All right, so we got to the important part. Sorry about that. Yeah, I don't know why. I must not have started it right. Probably because I'm sick. All right, so this is the diagram that you'll normally see in textbooks. It's just like what the Go Back In protocol looked like. So again, if you want to see that, you can go to the Extras folder. In the Extras lectures, go to Interactive Animations. It brings it up here. Here's Go Back In protocol. That's one. You can send a bunch of packets, and you can send them at different times. You can speed this whole thing up, and it'll send acknowledgments back. All right, so this is what they basically look like. The green ones have been done. You've forgotten about them. You've sent them. They've been acknowledged. You do not need to keep a copy of them anymore at the sending TCP software because they've been acknowledged. The yellow ones have been sent, but not yet acknowledged. So these are considered in-flight packets. These are ones that are flying around. You don't know if anybody's gotten them or not, but you're waiting. Your window, though, is even bigger than that. You have colored in blue some spaces where you could send more packets if you wanted to, but maybe the application up above doesn't have any right now, or maybe we just took a snapshot right in the middle of all this going on. Normally, you should assume the system has an infinite supply of packets to really understand how this stuff works. So there's some variables here. There's the base number, and there's the next sequence number, and then there's a window size. And you can continue to send packets until you fill the window. And then you got to wait for acknowledgments to come back. So the minute that send base plus n is less than next sequence number, it means your next sequence number is falling outside of this window. So what is this next sequence number thing about? We number every packet that goes out the door. But the truth is that TCP really tracks bytes. It doesn't track packets. The decision to put a certain number of bytes in a packet is really a decision that's negotiated between the sender and the receiver based on what's going on the network right now. So if you think that the network is relatively congested and you're worried your packets are going to get dropped, you may negotiate a smaller packet size to increase the odds that it'll slip through, even if there's like small spaces only left in router buffers. So that has nothing to do with sequence numbers. The sequence number is given to each individual byte. So TCP numbers every single byte. They start with a random number between 0 and 4 billion. So there's 16 bits to keep track of these things. And then you just kind of cycle through. You know, if you get to the end, you just start back over with packet 0 again. So when you put packets, when you put bytes in a packet, you put a number in the packet to let everybody know what are you starting with this packet. So you put the number of the first byte, and then you have some number of sequentially organized bytes. You'll never have gaps. The sender will always send a string of bytes together. So you'll have the first byte number and a quantity in every packet. So this has some big advantages to do it this way. One advantage is if you are going along somewhere and you reach a router that's connected to a network that just cannot handle big packets, like an ATM network can only handle 53 byte packets. You're going to need to take all of your byte passengers off of this boat and have them get on smaller ones to make the last thing. It's like when a cruise ship gets near the dock, and then sometimes you have to get on a little excursion boat to make it the last of the way in. So each one of those boats is going to have the same two things, the first byte number on the boat and how many people are on it, how many bytes are on it. So this byte number, first byte number and length lends itself to packets being fragmented and defragmented. The other thing that's interesting about this, and we get this back from the Go Back In, is because it will never accept a packet out of order, it's got a window size of 1. You must send it the one it's expecting. It has no place to buffer out of order packets because its buffer size is 1 packet. If you get something, an acknowledgement from it, it's a cumulative acknowledgement. And let me show you what that means. So here's a variation on what we did a minute ago that no one could see because I never shared the screen. All right, so let's start this up. 1, 2, 3, 4, 5. Oh, that's way too fast. All right, so I'm going to delete these acknowledgements. So can Go Back In send an acknowledgement for packet 9 if it didn't get packet 8, 7, and 6 as well? No, it can't. That's right, because it's got room for only one thing. the next thing. If you send it anything other than what it's expecting here, it'll drop it. So therefore, if you get an acknowledgement for 9, it's proof that it got everything before it, because it would never have sent you the acknowledgement for 9 had it not gotten it in order. In order means 8 arrived before 9, 7 arrived before 8, and so on. So let's see what happens to my window. What do you think is going to happen to this window up here? Yeah, all the way to the right. Right, so let's take a peek. Bam. So it's acknowledged. Great. So that is sometimes used, and it's something we use in TCP that we borrowed from this protocol, called a cumulative acknowledgement. On the other hand, if you go back and you look again at selective repeat has a timer and a bigger buffer at the receive side. So just because you get the acknowledgement for packet, I think there's a keyboard shortcut to do this. If you guys actually read the text on here and stuff, it'll help you out with it. So what's going to happen now? What's my window going to do here? It's not going to shift, right? Because the oldest thing in here, it's responsible for making sure everything in this window got delivered. That's why we have the window. These are packets that are in flight and as yet unacknowledged, and you want to not bother the program to give them to you again, so you are keeping a copy of the packets in this window. That's one reason why the window isn't infinite. You know, you just keep it manageable size. So with the selective repeat protocol, I'm totally okay with packets arriving out of order, and what this system will do is send acknowledgments in whatever order they show up. So as far as the sender knows, when he gets this acknowledgement for 4, it's the only one he got. And maybe 1 through 3 are right behind. He doesn't know why he only got 4. But it'll mark it as received, so it doesn't have to send it anymore. But it can't move the window, because if it slides the window to the right, it'll forget about one of the packets that hasn't been received. And then you lose your chance to resend it later if you need to. Okay. Meanwhile, back over. So that's what go back in looks like. If you look at the sender finite state machine, here's my next sequence number. So the next sequence number is like a number on the wall, now serving number 326. Packet shows up, a bunch of packets show up, they want to get on the boat and take a trip to the receiver. You have them get on the boat, you ask the first person, what's your packet number? And he goes, well, I was given this next sequence number as I was stepping onto the boat. Well, that's the one I need. I need you to tell me what that number is. And so everybody gets one of these little tickets. Everybody gets a ticket to get on the boat, and it's a sequential number. And the very first person puts theirs on the front of the boat, so everybody knows like who's on the boat. All right, so it's an endless stream of packets coming down like the analogy I usually use is passengers show up at the top on a train. The train empties out. Everybody goes to the escalator. They all start coming down the escalator to the underground boat launch, and they just wait their turn, and they get on boats depending on where they're going. It might be a different size boat, but they all get on there, and they stay in order, and they're all given numbers. So the message, the application shows up with a batch of traffic at a time, a train full of it, a message made with a function call, and then TCP has to take care of byte by byte, getting things, filling up boats and sending them off. Boat sizes may change because of the conditions of the water or the network. So the next sequence number is actually something I use to assign a byte its number. This is always the next number, now serving number 326. You guys have seen those signs in places before. So as long as my next sequence number still is inside the window, and inside the window means basically it's less than base plus n. Base plus n is this point right here. So as long as my next sequence number is less than that, then like here, for example, then I can send a packet, and I'll do so. And I start a timer for the overall task that I've done for the overall window. If the timer goes off, I go back to the very first thing in my window, all the way up to the very last thing in my window, and I resend all of it. That's what happens. So it's inefficient in that I send packets 1 through 10, and 1 is lost, 2 through 10 are delivered. It won't acknowledge any of them. It'll just keep saying, but I wanted 1, but I wanted 1, but I wanted 1. It's like, all right already. So you want 1. So it'll throw the rest of them out, And then you're doomed to resend packets that, in fact, successfully arrived. It's just the receiver refused to take them. So that's an inefficiency for it. If the packets are corrupt and you kind of drop the stuff, you resend and you set a timer. On the receiver side, as long as things are in the right order, in the right sequence, then you will send them back up to the application. You will deliver the data back upstairs, extract the data out of the packet, and has the right sequence number is true. So this is what you want to happen most of the time. If otherwise you get something that's not the right one, you'll just send the ACK back for the last ACK you did to let people know. All right, so it may be occurring to you that, you know, if I'm sending a bunch of packets and the other end keeps sending me the acknowledgement for the one it's missing, maybe I should figure that out. That's a hint. You know, if it keeps telling me, but I wanted one, but I wanted one, but I wanted one, well, maybe you should send it one. Maybe you don't need to wait for the timer to go off. Maybe if you're getting acknowledgments back for the other packets, maybe you should go ahead and resend one, because it's just kind of ruining things for it not to have one. So that's something we'll see in real TCP. Okay, go back in action. Here my window size in is 4. So I can send up to 4 things out at a time without getting acknowledgments back for any of them. But I'm going to stop at 4. I won't send a 5th one until I get an acknowledgement back. So I send 4 packets, 0, 1, 2, 3. Packet 2 is lost. This is go back in. So it's going to throw out packet 3. Why? It can't buffer it, and it's out of order. It expected 2. So it doesn't have the buffer space, right? So exactly right. So he will throw out, and he will resend the ACK for the last one he acknowledged. So you're going to get a duplicate ACK here in a minute. In the meantime, back at the sender, when somebody sends a 0 and gets an acknowledgement back, that moves your window over, because that was the leftmost thing in your window. So you can slide your window over. Now the number 4 is inside this rectangle, and fortunately you have an infinite supply of data from the program, so you can now and do in fact send packet 4. Now it's not going to have sequence number 4, it's going to have some random big number that's the first byte number, but to make things sane, we're just going to use numbers like this as if the packets were numbered, just so we don't lose our minds. We send packet 4. Immediately after sending packet 4, acknowledgement 1 arrives. So that slides our window over as well, and we can send packet 5. And so we'll do that. Meanwhile, packet 4 is also received at the receiver. It is also thrown out because it is still not packet 2. That's the one it needs next. Same thing with packet 5. It's going to throw that thing out. You'll get a duplicate ACK, which I'll ignore. Eventually, the timer for packet 2 will go off. And you'll go, geez, man, like I guess he's never going to give me the ACK. I'll resend it. So what will happen at that point is you'll resend the whole window, because you know with go back in, it threw everything else after that away because it didn't get 2 in order. Or it looks like it didn't get 2 in order. You didn't get an acknowledgement back. You don't really know whether the packet was lost or the acknowledgement was lost, but you do once you start getting these back, because had packet 2 arrived, it would have arrived right here, correct? And I would have sent acknowledgement 2 back. And let's say the acknowledgement was what was lost, not the packet. So I never got acknowledgement 2. Packet 3 shows up. It will send acknowledgement 3 because it got 2. So, and let's say ACK 3 gets lost. It will send acknowledgement 4, and that one I get. So when I got ACK 0 and ACK 1 and ACK 4, I'm okay with that. That's a cumulative acknowledgement. It never received things out of order. So for me to get 0, 1, and 4 means I must have gotten 0, 1, 2, and 3 so that he could then send 4, send me an acknowledgement back. All right, so that's kind of what's going on. Selective repeat keeps track of things individually. So this is quite interesting because it's a great example of how you never really know what's going on at the receiver. So if you take a peek here, you've got send base set to this value, and your in is this big, so your rectangle is this large. You're ready to send another packet. You have room to do it, and the sequence number of the first byte in that next packet is held by this variable. So everything looks all right, and I've gotten acknowledgments back for 4 of these packets. Those are the ones in green. So I haven't gotten ones for these 4. So I think maybe these packets could have been lost because they didn't get any acknowledgement back for them. In fact, it's often true that if you start getting acknowledgments back for later packets, like not the next one, but further away than that, like you did here, that probably these are lost. That's typically the case. It's not often that packets arrive out of order constantly like that. It's unusual. It happens. All right, so what really happened? Let's look down at the receiver. What really happened is he got all those packets up to this one. So he received these two, and obviously he sent acknowledgments back for them because he's moved his window over to the right. Now he doesn't have the job of resending anything. He just has the job of sending an acknowledgment, tries one time, and that's it. So the sender's the one that's got to hold on to the data. He has the harder job because the sender's the one that's got to send a copy of it again if he decides it's lost. The receiver's all the way over to here. He has not received this packet. We don't know why. We don't know if it was lost or if it's just slightly delayed and it's going to get there in just a moment. But inside the window that he has now, which is considerably over to the right, he's got 3 packets that he's received and sent acknowledgments for. 2 of them have been received by the sender, and they're green. 1 of them he sent back, and it's still showing as unacknowledged. Although, you know, this doesn't really, this is not correct. There's a bug in this diagram. I need to remember this. Hold on just a second, because I'm also trying to help Jim fix problems in this. That's not errata. Sorry, guys. You know, it's just so hard to write a textbook that if I do find something, he's been so good to us, to the University of Houston specifically. We got to beta this book for him before anybody else had their hands on it. So, like, I was super happy. Okay, slot L10 145. Let's do this. Let me selective repeat. Selective repeat diagram shows receiver acking a packet that the sender has not yet sent. Okay, thank you for your patience for that. Okay, selective repeat, we've gone over this. If you want to get the details and kind of step through it in text, you can. Here's the way selective repeat will work. Same scenario, we miss packet 2. We will not throw it away this time. We buffer it, and we send it acknowledgement 3. So if we continue on, we're going to send 4, we're going to send 5, and we'll send Act 3 has arrived, so we'll mark it down as having been received, but we can't really slide our window over all the way because we still haven't gotten the acknowledgement for 2. But we can send 4 and 5, and we'll get acknowledgements back for those. Timer 2 will go off, and when it does, it will be resent. Packet 2 will be resent to the receiver. What's going to happen at the receiver now? He's buffered packet 3, 4, and 5. Why did he buffer them? Because he received them, but he buffered them because he received them out of order. To be more specific, had he received them in order, he would have just delivered it to the application. So he's sitting on packets 3, 4, and 5. He finally gets 2. Now he's got a string of packets that are in order, right? So he'll send them. He'll send 2, 3, 4, and 5, and he'll acknowledge that he got, 2 back, I guess. So this is not cumulative acknowledgement. So he has to acknowledge the packets that he got. So the problem with this one is that if you miss an acknowledgement, which happens, they can get dropped, you're doomed to resending the packet. So we go back in, we didn't like that it threw a bunch of stuff away, but at least if ACKs were missing, if I got ACK 5, I could just slide my window over because I knew it got packets 1, 2, 3, and 4. Here, it'll buffer things for me, which is a plus. I don't resend stuff as often, except I can't deal with lost ACKs. So I need something that kind of goes in between these two and kind of helps figure things out. Meanwhile, the last step is when Act 2 arrives, this window on the sender side is going to slide all the way over to 6, 7, 8, whatever. Okay, a couple of famous problems with selective repeat. Suppose you have a window size of 3, and you have a number of sequence numbers that is larger. So at least it's bigger In this case, I have 4 sequence numbers. Do you see that? 0, 1, 2, and 3. And I have a window size that's smaller. So I'm going to send 0, 1, and 2 because that's my window size. N is equal to 3. And I send them. And I get an acknowledgement back for 0, and I get an acknowledgement back for 1, and I hopefully get an acknowledgement back for 2. But in the meantime, packet 3 is missing. So packet 3 doesn't make it. The receiver's window is advancing nicely as I send the packets over. It's receiving 0, sending an ACK, and then it moves past it. It's done. The receiver's finished. He doesn't buffer ACKs that he sent back. I mean, he's finished with. Once he sends the ACK back, then if it's on the left-hand side of the window, he moves the window over because he's delivered it to the program and he's finished. But in this particular case, it's interesting because 3 is not going to make it. But I've been receiving some ACKs, so I can continue to send things. I've slid my sender window over, and my sender window includes now this 0. So I'll send it. So the question is, does the receiver correctly understand that the 0 that he got is this one and not this one? Yes, because this is the one inside his window. So if he gets 0 instead of 3, which is exactly what's going to happen, 3 got lost, he will correctly think that it is the second round that's begun. However, there's a variation. What if you send 3 packets, all 3 acknowledgments get lost? The receiver is finished. He's slid his window over. He's ready for 3, 0, and 1. He's gotten these 3 packets already. But the sender never got the acknowledgments, right? So the timer's going to go off at the sender, and he's going to resend 0. So now I ask the same question. Will the receiver correctly interpret this time that the 0 that's being resent is this one down here, or will he misinterpret it as the second round getting started? So this is death. This is bad, bad, bad. You do not want this to happen. Why did this happen? What mistake did I make? What thing should I change in my variables that would keep this from happening? There's several answers, so you can pick one. What's the confusion here? What is it that tricked me? Yeah, the sequence numbers. I thought 1, 0 was another. Had this been sequence number 4 instead of 0 again, would I have had this problem? So maybe I should use more sequence numbers. Probably, hint, hint, there's a ratio of the number of sequence numbers you need to have to the maximum window size you're allowed to permit. If you tell me how big your biggest window can be, I can tell you how many sequence numbers you must have. Conversely, if you tell me how many sequence numbers you have, I can tell you then you cannot ever have a window bigger than this. And it's a ratio of sequence number, but I'll let you guys kind of get into that a little bit in the homework. Took me years to figure out what this was. It finally figured out it was an iron curtain, or like a curtain, because somebody pointed out there's like a curtain rod at the top. I thought it was a piece of bacon because that's what fat people think. And I thought it was like a piece of wood, and I went back to bacon because that sounded better. And then I finally figured out it was a curtain. So the idea they're trying to show you here is you can never know what's going on at the other side. Remember how I told you that? You can never really know what's happening on the other end. So you have to be careful about that relationship. Okay, so real TCP is fascinating and very, very rich. We have actually wonderful diagrams. If you guys like pictures about how protocols are working and things, you will love TCP because we've invented all kinds of wonderful stuff. In fact, I will tell you in Wireshark, there are awesome graphing tools that will map what's going on. None of them are in the Wireshark projects for the textbook, but I worked with a professor in Mexico who wrote some labs to do it, and I need to grab some of them and bring them up here because they're easy and fun. And it's a really good thing to know that Wireshark can actually plot what's going on, because that's, as a network designer, very often how you will first see what's going wrong on a network, is if somebody can put a picture in front of you. So TCP sends things bidirectionally. When you open a connection, of course, you're not just sending things to one person, they're sending things back. And we will only use one direction so that we all do not go insane in this class. And then it's connection oriented, so that's what TCP does to make sure it has permission. It does flow control, so every single time you send a packet to the other side, it tells you, okay, got it in there, here's how much space I have left in my buffer. So don't send me more than this. So before you fill up a truck with 10,000 pounds of sugar and send it over to the restaurant, you might want to check to make sure they have enough shelf space for it. Because you have an infinite supply of sugar to send. Right? You're the sender. So it's an infinite supply. So you have to be careful not to send more at a time than the receiver can happen. And I can actually show you this with Wireshark. So what I'm going to do is capture a few moments of Wireshark. But it would help if I use the right interface. There we go. So we'll let this go, and while that's going, I'm going to go up and reload a web page in here as well. All right. What I need to do is stop the capture. Okay. So what I want to do is sort. So I just get the TCP, and there's a bunch in here. So I'm going to pick one. I'm going to open up the TCP part of Wireshark. So it starts at layer 1, 2, 3, 4. That's the way Wireshark works. And in here is the window size of 2428. Do you see that? So it's going to turn gray because I'm going to move my focus to the top. And as I scroll through here, look at that gray stripe and how the size has changed. 2048, 8192, 2076, 70. A lot of them are 8192 because those are to a specific server at WebEx. But the rest of these things, they're like all over the map. They're changing, especially if I get down to some of these near the end where I was dealing with the application that was running, the animation. I just saw a 1900 one in there. Did you guys see that fly by? There it is. So every single time you send a packet, it changes. Now, if it's a server with tons of resources, maybe it can always accept the same amount and it doesn't ever have to tell US. It's a big server, but most of the time these things will change, especially if you're dealing with just another user, like with BitTorrent, for example. All right, so that's fun that you can actually see those window sizes changes. It's point to point. Thank God we don't do this with like a fan out of 15 receivers. It's one person at a time, and it provides reliable in-byte order as a stream. It's pipelined, which means it's going to have multiple packets in a window that get sent out at a time, all in flight, as yet unacknowledged. You're going to wait for the acknowledgments to come back. Here's what the TCP header looks like. It's considerably more sophisticated than the UDP one. I have flags in here to do things like negotiate the connection. So some of these are used to say, I'm trying to make a handshake with you, or I'd like to shut the connection down. So those flags can get set. There's always room for a sequence number of what you are sending, as well as room in every packet for an acknowledgement number, should you need it, for packets that you've received from the other side. So while you're sending a packet to them, it's a great time to acknowledge that you've already received something else. So that's why there's a space in here. You have to set the acknowledgement flag, however, to let them know to pay attention. Because an acknowledgement number could be 0, and it will always be 0 if you haven't put anything in there. So if you actually mean for people to pay attention to it, you have to set this flag. So while I'm talking to you and you're talking to me, I'm giving you new info and acknowledging what you just sent back to me. Thank you for your letter of yesterday. I've looked into the information and here's my response to you. You mail it. The person at the other side says, thank you for that extra detail. They're acknowledging what they just received from you, right? And every letter you send someone, if you're responding, you will acknowledge what you received. So TCP works the same way. All this slide is telling you is we're dealing with byte numbers, not packet numbers. So we draw these as packets. We put numbers on them like they're packets. When you have exercises, you'll be dealing with packets, just so we don't go crazy trying to draw it. It's too hard to draw the bytes. But just know all we're really doing is sending bytes. So these packet sizes can change. So they may be tall and short and tall again and short. You know, all depends. Okay, so outgoing, when you send something, here's a change from go back in. Remember when I showed you if the first packet got lost and it's supposed to send you the acknowledgement for the last one that it got? There wasn't a last one. Do you guys remember that when we looked at it? Let me see if I can find it again. I think it's, go back in. have to shut some of these down. Yeah, it doesn't remember. All right, so I'll show it to you again. So the problem with go back in with acknowledgements was it always sends you the acknowledgement of the last packet it received. But if the last packet it received was nothing, like I'm going to kill off packet 0, then it can't send you an ACK at all. And that's not good because now I think the network's completely down. And what I will do when I think that is very different than what I'll do if I think there's just one packet missing out of the string. So I'm going to send the sequence number with real TCP, but I'm going to send you the sequence number not of the last thing I got, but I'm going to change it. I'm going to send you the sequence number of the next byte number I'm ready to receive. Important difference. I'm going to always send you the acknowledgement of the next one I'm ready to receive. So you see this sequence number in here points to this blue bar because that's the next thing I'm going to fill up and next boat I'm going to launch. And on the receive side, you'll do the same thing. You'll send the acknowledgement back for the next one you're ready to receive. Okay, so let me show you a diagram because I think I'm saying this a little bit confusingly. So host A and B have been communicating for a while. They both rolled a die and picked a random starting sequence number. They don't start with 0. But well, for whatever reason, maybe because they picked things that were close to each other or they picked things that were small, right now they're on 42 and 79. What can I really conclude from that? Nothing. Host A may have started at 800 and has sent so much data, he's wrapped around all the way back to 42 again. 4 billion bytes. Whereas host B may have started at 70 and now he's at 79. He sent nothing all day long. You can't tell where people started by looking at a sequence number. It's impossible. All I know is that host A is now going to send a stream of data to host B starting with byte number 42. So he puts sequence number 42 in there. And he's also going to acknowledge something that he got earlier. We're going to ignore that for a minute. B receives the packet, and he sends an acknowledgement back, thank you for your packet of Tuesday, and he sends back the next byte number he's expecting to receive, 43. So this was a packet that only had 1 byte in it, which is also kind of odd. But do you guys know the program Telnet? Telnet is a program that you can use to log into a remote host. You'll usually use Secure Shell these days. But Telnet is, Telnet's been around forever. Telnet is an interesting program because every keystroke gets sent in its own packet. So Telnet to, let's see if this will work. I doubt it will. Oh, it doesn't even like Telnet anymore with the latest release of OS because I updated. Yeah, so Telnet's going away because it's not considered reliable. But the thing I like about it is it puts every byte in its own packet. So we used to use this for everything. We used to use this to log into remote Unix machines, and you type in your username and password and hit return. And it was interesting because you could tell that it was sending 1 byte at a time because when you type the key, it would take a minute for the character to show up on your screen. It wasn't like with Microsoft Word where you type and the characters show up. It would take a moment, sometimes quite visibly noticeable. And the reason was that it would not display the character that you typed until it received the acknowledgement back for it. So you knew that it had been delivered, which is kind of handy. It was kind of clever. So A sends a packet with 1 byte of payload to B. It starts with sequence 42. He acknowledges sequence 43. Meanwhile, host B had sent some data to A that ended with byte number 78. It was the last byte number in the packet. Doesn't mean that it was the byte number on the front of the boat, but it could have been if it only had 1, but it ended with 78. So he's going to acknowledge that I'm ready for 79 and beyond. Dun, 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 right? So 79, he sends him something with 79, and he acknowledges, got it, now send me 80. So these are unusual because they're only 1 byte. Normally these numbers are big. So round trip time, how do you know how to set a timer? The blue dots on this are called samples. With every packet, you get an acknowledgement back. You are measuring how long it took to get the ACK back. You don't get ACKs back for everything, but the ones you do, you're making note of how long, what the round trip time was. And these blue dots are showing you that data. So what you want to do is watch what's going on with your network. And if this average seems to be moving up, it means the time it takes to get acknowledgments back is going up. It means your network is getting slower. What it really means is that packets are waiting a little longer in buffers inside of routers along the way, and it's causing it to take longer. Nothing's changing the propagation speed. No one's pulling the network and stretching it out and making it take longer to get there, anything like that. So what you don't want to do is respond to sometimes what is the spastic nature of this by changing your round trip time. So you will average it. And the rule that we generally use is the next timeout value that we will set, so it changes potentially with every single packet, the timer value. I'm going to make it 1/8 of what it is now and 7/8 of what it was before. So if you get a big giant one like this that's way out of range, you'll go up, but only by 1/8 the difference between here and here, to try and use like a damping algorithm so you don't change. So the problem with this is sometimes the network is really doing this. And if you don't set your timer any bigger than this, you could be resending packets needlessly. So it's hard to know what to do to set the timer to, because this is in fact how long one packet took to get there. Why should I believe that it's not the new timeout value? Well, because we have enough experience that we know that it looks like this. In fact, the network looks better to me over here than it does over here. Why? The left side looks better than the right side. Why? What's different about the graph on the left and on the right? More consistent, less standard deviation. So we did add a standard deviation value to this to try and deal, whoops, wrong click. Let's try here. To try to deal with what happens when, we want to give ourselves a little bit of safety margin. So yeah, we'll go up by 1/8, but then we'll go up by a little more too. If the standard deviation is really crazy, then we'll add more to the timeout value because it makes us nervous. It means the network is unpredictable. Okay, so that's sort of what's going on. All right, we talked about a lot of this stuff before, and we talked about events. What I just want to make sure of is that I haven't gone too far. Okay, so we need to stop now and switch gears and talk about something else. And we're going to finish, I think, way early, unfortunately. That's partly because I'm scared about my battery, because I broke my power supply finally. And so I have to go by the UPS store, which doesn't open until 10, blah, 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 blah. Thank God there's one there waiting, etc. So we have an exam in a week, and I'm behind on homeworks. So I don't like giving an exam with only a couple of homeworks out. So here's what I negotiated with the class last night, and I need to know if you guys are okay with this. Okay, so first thing we talked about was, would you rather have the midterm before or after spring break? And with the exception out of 25 people of 1 or 2, everyone wanted to have it before. They didn't want to have it over spring break. So does that sound reasonable? All right, so my job then is to make sure you're prepared for it. So I'm going to give you a homework. I have 2 ready to drop, and I literally fell asleep on my keyboard last night. I mean, my partner had to come in and say, it's time to go to bed, because I was sick, right? So I literally collapsed on my keyboard. Thank gosh we don't have raised letters on keyboards anymore. We used to. Every key had like a little raised, embossed version of the letter. And so we would call that QWERTY face, because the keys on your keyboard, top row QWERTY, this is the QWERTY keyboard. So if you fell asleep on your keyboard, you'd wake up and you'd have the imprint of QWERTY on your face. So I had a bad case of QWERTY face last night. That's what we called it. We had a bunch of other ones. Another one had to do with computer architecture, where we'd have a program error called PIBKEC. It stood for problem between keyboard and chair. So if you did something really stupid, then it says, oh, well, that's the PIBKEC error. Like, what's that? Well, you need to think about that for a while. So a lot of fun things like that. You guys can use all this stuff. I don't own the copyright on any of it. So there's 2 homeworks ready to ship out. I'll give you one today, this morning, that will be due on Saturday. So we talked about, should it be due on Friday, Saturday, or Sunday? So we decided on Saturday night at midnight so that the solution could be released and you at least had Sunday to study. Now you guys have an advantage because you also have Monday to study. The class yesterday doesn't. But I mean, really, you only have a few more hours to study because their class is at the end of the day and yours is the very next morning. So Saturday night means you'll have all day Sunday. So that's going to be one homework, and we've talked about a lot of the stuff on that homework here right now. The second homework we'll do in class together on Thursday on WebEx. So if you show up to the WebEx or listen in afterwards, you'll be able to finish that homework. Turn anything in, and you'll get 100 for that homework. But you need to know the material because that's what some of the exam questions will come out of. So that's a way that I'll make sure you're done. That one will be due on Friday, so you'll have one day to kind of clean it up. There'll probably be some things, stragglers, that we didn't get totally to that you'll need to kind of clean up, but I'll give you kind of the idea. And you can make that one due on Friday. So the first homework is due after the second homework is due. And on one of the homeworks, you're going to have a problem that's not due until after spring break. It's 20 extra bonus points that I promised you guys. So there'll be 20 points there for installing Mailcatcher, which we talked about a couple of weeks ago. Remember? That homework should have been released a couple of weeks ago, and it's just been one thing after the other. So that one I'm not going to make due until after spring break, and it's fun. So if you can't get it installed, you know, if you're really a computer scientist, you're not going to be happy with that. You're going to keep at it until you figure out what in the world's going wrong, or try different computers. So I want to give you time to noodle around with that. If you can't get it installed, it's an experimental problem. Show me, give me screen dumps to show me you tried hard to get it done, and you'll still get the full points for that problem, right? But I want you to work on it. I want you to do stuff. So that's what we're going to have from here until next Monday. Next Tuesday for you guys, we'll have an exam. It'll be short. It's going to take an hour. I'm not going to make it, you know, a killer. I like for the homeworks to really be a better representation of what you're learning because you have a lot more time that you can spend on those if you get stuck on something. The test, I'm more interested in seeing if you know what the mechanics are than if you can do the math perfectly every single time. So if I give you a problem that says you have a 500,000 bit file and you need to send it over a 2 megabit per second network for 48 kilometers, how long is it going to take to get to the other end? If you do the right formula, but you screw up the math, you get almost all the points. You might lose a point for that. You're not going to get a 0 points for that problem. Because that's not what I care about. You'll use calculators in real life and Excel spreadsheets and things like that. But you won't if you don't know the formula. So you can bring a cheat sheet to the exam. So please make a cheat sheet as you go along. If there's formulas that you see through the homework or things you want to bring with you, I don't care if you cut them out with a pair of scissors and glue them on this sheet, or machine print it, or you guys get together on WhatsApp and come up with like the single ecumenical best cheat sheet ever in the history. Just remember, the more stuff you put on the cheat sheet, the more time you're going to waste reading it. My experience, year after year after year, talking to thousands of students, has been making the cheat sheet raises your score, not using it. Because making the cheat sheet makes you remember the thing, right? You're committing it to memory by writing it down again. Well, we all know that, right? That's the way this stuff works. So, but you can bring that, and then if I do get a study guide out the door that's reasonable, you can bring that too. And I will tell you when I send the study guide, you really need to make sure, absolutely, you print this and bring it. Bring a calculator, bring something to write with. It'll be helpful if the calculator can do basic stuff. You will not need to go between binary and decimal and hex like you did in computer architecture. So any calculator will work for this type of exam. I will always bring, if I'm sane enough to remember, I'm not sick, calculators and extra copies of everything, extra copies of the study guides, for example. So you'll have them. So we'll do that together on Tuesday. Sound all right? Yeah. Sure.
So we are going to go over for the exam 1, 2, 3, and 4.
Yes, the exam will cover the 4 homeworks, 2 that you've done, 2 that you will. And to give you time for the homework 4, we'll just do it together in class on Wednesday. And I'll try to reserve some time to go over some of the problems on the other 3 that I think we'll have on the exam. What that may mean is that I end up going over a problem on homework 3 that you haven't done yet. And it's like freebie, you know, you get the next one, but that's our last time to talk before the test, and I'm not going to send you in blind. I work with a professor who basically says, I assigned you the textbook. Anything in the textbook is fair game. Like, I'm not that person. I know they're there. I get it. I've had them. I'm not going to do that. I don't do that. I'll tell you what's going to be on the exam. It's hard enough. so you can prepare for those things, because I want you to come in and do well on exams. I'm not, I'm not sadistic. I'm not trying to show you that I'm smarter than you, because I'm not, or better than you, because I'm not. I'm you, basically. So we'll get through these kinds of things together. I've done it a long time, so I'm good at it, but, all I have as an advantage is I'm older. That's it. Not better. So I remember that. So you guys will know what's going to be on the test coming up, and you'll be able to do okay on it. All right? Okay, other questions? All right, let me check the chat and make sure I'm not missing stuff out there. Gracias or crash. I know Skynet, yes. Sorry about that. Hey guys, next time you can't see the screen, do me a favor and unmute. I don't care if you're in a noisy background or what, and just say, can't see the screen, or excuse me, or something like that. And I'll, because I just messed up if I don't do that. All right, other questions? All right, I will take my QWERTY face and my little squeaky little laptop holder here and go grab my power cord and just leave. I'm just going to go to Mexico then. All right, thank you guys very much. I'll see you in class on Thursday, okay? Got you out here a little early. That's what being nervous about power will do for you. My old battery, there's no way I could have ever made it like 30 minutes. It would have never happened.